Okay, so let's begin with some group theory. First of all, we'll learn some very basic things about groups. The book I'm following is the Algebra book by Michael Artin. It's a very good book on algebra. It's one of the best books that I've found, and I also recommend you to learn from this book. So we'll be following this book, and so first of all, we start with the definitions of group and abelian groups, and then we talk about the additive and multiplicative notations, which are the two notations used for groups. And then we review some very basic theorems about groups, some of the very basic ones. And then, as an example, we give an example of a group which is a general linear group, GLN. So we talk about this because it is an important group in group theory, and we will talk much more about this and its subgroups much later. So then, after this, we talk about permutations and an important group of permutations which is known as the symmetric group Sn. Then we talk about subgroups. What is a subgroup? And in particular, we will also study the subgroups of integers. And here, actually, since we are dealing with integers, here we will deduce some very good, very important, and quite non-intuitive properties of integers, and some really good results from group theory, and the very basic results from group theory we will derive it. And here we also will see how powerful is algebra. So by using the concepts of groups and subgroups, it is quite easy to deduce all these basic properties of numbers. But otherwise, the same properties, if we don't use the concept of groups and subgroups, it looks a really difficult problem to do so. Right? Some theorems that are really non-intuitive will be derived by applications of group theory to the group of two integers, right? Okay, so first of all, we begin with the definition of a group. A group is a set on which a binary operation is defined. So a binary operation is just an operation which assigns any two elements of the set G to a third element. So such an operation is known as a binary operation on the set G. So more formally, we can say that a binary operation is a map from G cross G to G, so which means it assigns an ordered pair of the form AB, where A and B are the elements of the group, to an element C of G. So such a map is a binary operation. So any two elements, it associates third element C of the group. So a group is a set on which a binary operation is defined, and it satisfies the three properties. So the first property is associativity, that if we have A, B and C are three elements of a group, and first composing A with B, then composing the result with C will give the same element as composing A with the result of composing B with C. And secondly, the existence of identity element. G contains an identity element, which means that an element which either multiplied on the right or on the left of any element of G will give the same element of G. So if A is an element of G, then A times E equals E times A equals A, right? So such an identity element in G exists. And the third property is the existence of inverses. For each element A, there exists an inverse element of A, so which we can call B. And inverse means that if we compose A with the inverse to the right or to the left, so A circle B equals B circle A equals E, right? So it will give us the identity element. So that's the inverse of A, right? So for each element of A, the inverse elements also, its inverse element also exists, and we can denote the inverse elements by A inverse, A to the minus 1, right? It's more often be denoted by this symbol, A to the minus 1, A inverse. And the group will often be denoted by G circle. So because it consists of two things, one is the set and other the binary operation, so it is reasonable to denote it by this ordered G circle. And also we can just denote it by G if the binary operation is clear from the context and it's obvious what the binary operation is. Then we don't need to just write we don't need to mention the operation as well. Just we can write the symbol for the set of on which the binary operation is defined, right? So that was the definition of a group. And as we see, the group is quite a simple algebraic structure as compared to other algebraic structures like the field or a vector space. A field involves a one set and two binary operations. One is addition and other is multiplication. And it satisfies more than three properties. The binary operations in the field satisfies much more than three operations. And also in the vector spaces, it consists of two sets. One is a set of vectors and other is a field over which a vector space is defined. So, and also the two binary operations are there in the vector space. The first is the addition between vectors and second is the scalar multiplication between an element of a field and an element from a set of vectors. Right, so compared to that, these two structures, fields and vector spaces, group is quite a simple algebraic structure, and that's why we see that why we study the study of algebra by the group. So it's quite a simple algebraic structure to deal with. So next we move on to abelian groups. So an abelian group is just a group where just one more additional property holds that the binary operation is commutative, which means A circle B is equal to B circle A for all A, B, and G. So if the binary operation of the group is commutative, we call such a group an abelian group. Okay, so now we are done with the definition of group and abelian group. So move on to additive and multiplicative notations that are used in a group. So we basically use two notations. One is the additive notation and the other one is the multiplicative notations we use for a group. Right? So like this A circle B, right, is a result of composing A with B. In multiplicative notation, we can simply write it as AB. And in additive notation, this can be written as A plus B. And also A to the n. So by A to the n we mean multiply A by itself n times, right? And multiplicative notation it is A to the n power n, and in additive notation it is n times A. So n times A is just adding A n times, right? Which both means basically the same. Multiplying A by itself n times and adding A to itself by n times is just the same that composing A to itself by n times. Composing A with itself n times, and the composition being the binary operation of the group. Right. So in this additive multiplication and additive notations, we write it like this. And so the inverse element, right? As we have just seen, the inverse element in multiplicative notation is written as A to the minus 1, but in additive notation it will be written as minus A. And also by A to the minus n, A to the power minus n, we mean multiply inverse of A by itself n times. So A to the minus n is A inverse times A inverse up to, and also till n times, right? Multiply A inverse by itself n times. And the same thing in additive notation is minus n A, which means exactly the same thing, which means the additive inverse of A n times, right? The inverse element of A to itself n times, right? And next, the identity element in multiplicative notation is denoted by the symbol 1, and in additive notation it is denoted by the symbol 0. So remember here, the 1 and 0 are not the real numbers 1 and 0. It can be, but they need not necessarily be, because a group can contain either numbers or can be a group of functions, it can be a group of any other abstract objects. So it's just that when we use multiplicative notation, we denote the identity element by 1, by the symbol 1. And when we use additive notation for the group, we use the symbol 0 for the identity element. So it's just just a symbol that we are using it, right? And now we have defined the powers. What is a to the n? So you can easily verify the laws of exponents, the very usual and familiar laws of exponents. A to the r times a to the s is equal to a to the r plus s, right? And you can verify this yourself, and it's quite an easy thing to verify. And other things, a to the r times s, a to the r to the s is a to the power r times s, right? And you can easily translate it to additive notation, like for example, a to the r times a to the s becomes ra times sa, then it equals r plus s times a. So yeah, it's quite easy to translate it from one notation to another, and you should be familiarizing yourself with this, right? Okay, so next move on to some examples of group. So first example, I will start with an important example of groups in group theory, which is the general linear group GLN, which is the group of invertible n by n matrices, and the matrix multiplication is the binary operation of the group. So the group of n by n invertible matrices with matrix multiplication as the binary operation is called the general linear group GLN. So it is an important group, and we can verify it is a group, right? So first of all, we can verify each of the group properties. So first of all, if we multiply an n by n matrix by itself by another n by n matrix, then it results in another n by n matrix, right? And also, if when we are multiplying two invertible n by n matrices, then the result is also an invertible n by n matrix, because this is a basic fact we learned from linear algebra, that the product of invertible matrices is an invertible matrix. So if you multiply any two elements from this group, any two invertible n by n matrices, it will give another invertible n by n matrix. So this is closed under that matrix multiplication. This set is closed under that multiplication, and so this matrix multiplication, we can say, is defined on this set. And next, okay, so we can move on here. Okay, next we have to verify these three properties. So does the associative law holds? Yes, obviously, because the matrix multiplication is associative, right? We know this from linear algebra. And does it contains an identity element? So the n by n identity matrix is an identity element of the group, right? Because any matrix multiplied by the identity matrix either to the right or to the left will result in the same matrix, right? So any matrix A times identity equals identity times A equals the matrix A itself. So the property 2 is also satisfied. And now we check property 3. So for each invertible n by n matrix in the group, is it true that an inverse matrix exists? And which is obviously true, because we are talking about a group of a set of invertible n by n matrices. So if you are considering a set of invertible n by n matrices, then obviously each of these matrices has an inverse. So all these three group properties are satisfied, and obviously a matrix, the matrix multiplication, which is the binary of operation of the group of the set, is also defined on the set. So therefore, we can say that this group is this set is a group. So the group of the set of invertible n by n matrices under the operation of matrix multiplication is a group, and we call this group general linear group GLN. Okay, so next, the set of non-zero real numbers from an abelian group under multiplication. So we are talking about this set R star under the binary operation of multiplication. So R star I mean the set of all non-zero real numbers, which is R minus 0. So it is also a group, right? Because yeah, many of the three properties of the group can be verified because the real numbers is a field, and from the field axioms and the properties which come from the field axioms, the basic properties of the real numbers, we can verify all the three properties, right? Obviously, it's the product of two real numbers is a real number, so this binary operation is defined on the set, as well as the real number, the multiplication of real numbers is associative, which is elementary fact we know about real numbers, and also an identity element. One is not the real number. One is an identity element. So any number multiplied by one is the same number again, and also inverse exists because we are talking about the group of non-zero real numbers. So for each of them, any if the non-zero number, then real number, then its inverse exists. So this is one of the field axioms, right? So inverse also exists, and therefore R under this binary operation of multiplication is a group. Okay, so another example is the set of integers. Yeah, it's a very important set, important group. The set of integers from an abelian group under addition. One of the very basic and somewhat important group, right? Which we will just see. Which we will just study this group Z plus later in this video. So this forms an abelian group, right? So okay, so number two, the set of non-zero real numbers under multiplication is an abelian group because the real numbers, the multiplication of real numbers is commutative as well. A times b equals b times a for any real numbers n. So I just forgot to mention this property when I was discussing about this. So now I have done that. And for this as well, the number three, the set of integers also form an abelian group under addition, which you can yourself verify. It's quite easy. You have to verify all the three group axioms as well as see that if it's closed. Okay, so now R, the set of real numbers under multiplication, is not a group. Why is it not a group? Right, so think about it yourself. Why the set of all real numbers under addition is not a group? Right, so the group, so it has for the group there are two things: a set and binary operation defined on the set. So multiplication obviously is defined on real numbers. So it is not a group because one of the three properties fail to hold. Any of the three properties fail to hold, then it is not a group. So for the case of the real numbers, all the real numbers under the binary operation of multiplication, we easily see that the element 0 does not have an inverse, right? So the inverse of 0 is not defined. Therefore, this set of all real numbers under the operation of multiplication is not a group, right? And there are many more examples of groups, and so now we will turn to some very basic properties, very basic theorems about group. So the first one is let G be a group and A be the elements of G. Then the following properties hold. First of all, the inverse element the inverse of an element A is unique. So if A is an element of a group G, its inverse is unique. And the second one is the identity element of the group is unique. So there is just one identity element of the group. There cannot be more than one identity elements of the group. And next is A B inverse. The inverse of A times B is B inverse times A inverse, and the inverse of A inverse is the element A itself. Right. So we now prove this. So first of all, inverse of an element A is unique. So let B and B prime, they be inverses of A. So we consider B and B prime are the inverses of A. Then we can write B prime as B prime times AB, because AB is because B is an inverse of A. So A times B is identity, and identity times B prime is B prime. So B prime equals A times B. And now using the associative law, right, we can write it as b prime times a and then multiply it with b. And now since b prime is an inverse of a, so b prime times a is an identity element, and identity times b is b, right? So what this equation says is b prime equals b, right? So if b and b prime are inverses, then b prime equals b, which means the inverse is unique. Inverse of each element is unique, right? And second, the similar thing the similar strategy we use for the second thing as well. So if E and E prime are the identity elements of the group, then E prime equals E prime times E, because of the fact that E is an identity element of the group. So E prime equals E prime times E, right? And also since E prime is also an identity element, so this E prime times E is also equal to E, because E prime is also an identity element, and identity element times any element is the element itself, right? So we have this equation E prime equals E, right? So the identity elements is also, and the identity element of a group is also unique. And the third property is also a very basic proof. So we start with multiplying B inverse A inverse with AB, right? In order to prove that in the inverse of AB is B inverse A inverse, we have to check it by multiplying with AB. So first we will multiply to the left and then we'll multiply to the right and see if we can get identity element. So multiplying to the left, B inverse A inverse times AB equals B inverse times A inverse A times B because of the associative law. Okay, we can write it like this, and A inverse A is the identity. So we are just left with B inverse times B, and B inverse B is the identity E. So multiplying B inverse A inverse to AB to the left results in identity. Now we do the same by multiplying it to the right. So AB times B inverse A inverse, again by using the associative law we can write it as A times B inverse times A inverse, and which reduces to A times A inverse, and which is the identity element. So multiplying B inverse A inverse to AB both on the left and right results in the identity elements. Therefore B inverse A inverse is the inverse of B. So AB, the inverse of AB is B inverse A inverse, right? So we have proved all these properties, and they were quite basic and simple, and I can expect you to prove it for yourself, right? So, but since it was the first theorems that we were proving, so I decided to do it. And second theorem is the cancellation law. It's also a very basic theorem, and one of the very basic and one of the familiar ones as well, right? Not in the context of group, but in the context of numbers, real numbers. We know these cancellation laws, and we are familiar with it from the very beginning. So it says that let G be a group and let A, B, C be in G. Then if AB equals AC, or if BA equals CA, then B equals C. So this is the cancellation law. So in first equation, AB equals AC, we cancel A on the left and we end up with B equals C. And then in second equation, we cancel the same element A on the right and it end up with B equals C. Okay, so what is the proof? So the proof is very simple. Multiply both sides of the equation AB equals AC on the left by A inverse, right? So A inverse A times B is just B, and then A inverse A times C is just C, and we end up with B equals C, right? And to prove this equation, BA equals to CA, and you can do it yourself. The same things, which is multiplication by inverse. We have to multiply both sides of this equation, BA equals to CA, by A inverse on the right. Right? You get B equals to C again. So it's quite simple. And now one more concept is the order of a group. The order of a group, by the order of a group we mean how many elements are there in a group. So the number of elements in a group is the order of a group, and it's denoted by this symbol G with the bars, right? Next, Okay, so there are two kinds of group: finite groups and infinite group. If the order of the group is finite, means if there are finite number of elements in the group, then we call it a finite group. Otherwise, it is an infinite group if the number of elements are infinite in the group. Okay, so now we come to permutations. Okay, so first of all, we start with the definition of a permutation. So permutation is just a function. Okay, so let T be a set. A function f from T to itself is invertible if and only if it is bijective, means it is one to one and non to both. So for such a function, we call such a function a permutation of T. Right? So a permutation of a set T is a function from T to itself which is invertible, right? Or bijective, equivalent. And this fact, the function is invertible if and only if it is bijective. This is quite a basic fact which I assume that you already know, and if you don't know, then it is very easy to verify it yourself, right? It's not a very difficult thing to verify. You can verify it for yourself that if a function is invertible, this statement is equivalent to the function being bijective, meaning both one to one and non to. Right? A set of permutations of T form a group under function composition. Right? This statement, the set of permutations. So if T is a set, the set of all permutations of T. So if you consider the set of all permutations of T and the binary operations being function composition, then this is a group. Okay? And you can verify this yourself. Yeah? It is quite an easy thing to verify. Just the three group axioms. Just check them one by one, and you can verify it yourself. It's quite a simple thing to verify. So try it as an exercise. Okay, so the next, we now come to the symmetric group Sn. So the symmetric group is just a permutation where the set is the set of indices 1 to n, 1, 2, 3 up till n. Yeah. So the set of indices, if you're talking about the permutations of the set of indices, then this is called the symmetric group Sn. If there are n indices, then the permutation of these set of n indices is the symmetric group called Sn. Right? And obviously, this is the binary operation is a function composition for this group. Okay, next, like we talk more about permutations, and we talk about the cycle form of permutations. So we begin with an example of a permutation. So consider the permutation of S5. So this is the permutation from S5, where 1 is mapped to 3, 2 is mapped to 5, 3 is mapped to 4, 4 is mapped to 1, and 5 is mapped to 2. So as you can see, this is a one-to-one and onto function from the set of indices 1, 2, 3, 4, 5 to itself. So it is a permutation of this set, so from S5, right? And now in cycle form, how do we write it in cycle form? In cycle form, we write it. Suppose we begin with the smallest index first. The smallest index is 1, and 1 is mapped to 3. So beside 1, we write 3, and then we don't jump to 2, right? We take 3. So first 1 is mapped to 3, so we write 1, and then beside it we write 3, and then we see what is 3 mapped to. 3 is mapped to 4, right? Then beside 3 we write 4, and then 4 again, and 4 is mapped to 1. Since 1 is the first element of this cycle, so we just close this cycle here. 1 is mapped to 3, so this just consider this, right? This first pair. This first pair, if you consider it, it says 1 is mapped to 3, 3 is mapped to 4, and 4 is mapped to back to 1. So the last element is mapped to the first element, right? So you started with 1 or the smallest index, and then see that 1 is mapped to 3, so you write 3, and then 3 is mapped to 4, then you write 4, and then 4 is mapped to 1 back again, which is the first index. So we close the cycle here, and then we look at indices which have not appeared yet. So 1, 3, 4 have appeared. The remaining are 2 and 5. So again, we start with the smaller index first. 2. We start with 2, and then we see 2 is mapped to 5, so we write 5, and then 5 is mapped to 2 back again. So we close this cycle here, and this means 2 is mapped to 5, and 5 is mapped to back. 5 is mapped to 2 back again. So in cycle form, we write the permutation like this. This is quite a simple way to write, right? Quite a simple and effective. Like this thing, if we write it, requires quite some space, right? Even if we write it in a table, it takes some space. But this is compact notation, and it is very useful. Many times it is very useful. And obviously, we can also write this 1, 3, 4 cycle as 3, 4, 1, right? 3, 4, 1 because it means the same thing, right? 3 is mapped to 4, 4 is mapped to 1, and 1 is mapped to back to 3, right? It's the same. 1 is mapped to 3 here. 3, 4, 1, and also we can write it as 4, 1, 3 as well. This first cycle. So this thing is known as a cycle, right? This thing in a bracket 1, 3, 4 is known as one cycle. So this function f has two disjoint cycles, 1, 3, 4 and 2, 5. And I am saying disjoint because none of the cycles have the same elements in them. They have all the different elements. So these are disjoint cycles. So function f we can write it as 3, 4, 1, 2, 5, and 2, 5 we can also write it as 5, 2. So we can also write it as 4, 1, 3, 5, 2. 5, 2 means exactly the same thing. 5 is mapped to 2 and 2 is mapped to 5. Right, so there are various ways of doing this, but the standard way of doing is the first one. So the standard way is first you begin each cycle with the smallest number. So in each cycle, the smallest number appears first. So let's say if 3, 4, 1, the smallest number is 1, but this cycle starting with 3, so it's not in the standard form. So 1, 3, 4 is in the standard form because the smallest number is 1 and it begins with 1. And similarly for the second one, the smallest number is 2 and it begins with 2. And also which cycle to write first. We can also write 2, 5 then 1, 3, 4. Right, first 2, 5 and then followed by 1, 3, 4. But that will not be a standard way because the cycle which contains the smaller number first, which first entry is the smaller one, appears first. So 1, 3, 4 and 2, 5 are 2. Okay, so consider these two distant cycles 1, 3, 4 and 2, 5 here. So if we write 2, 5 first and then 1, 3, 4, then 2 is a bigger and 1 is a smaller. So it will not be in a standard form. The standard form will be write the cycle which is already first of all in the standard form, and the smaller number, the first entry which the cycle whose first entry is the smaller appears first. So 1, 3, 4, 2, 5. This is a standard way of writing, right? So I think we have spent enough time on these permutations. And one more important thing I need to talk about these permutations is permutations is just a function, right? From these indexes 1 to n of these indexes, from 1 to n to the same set bracket itself, right? So is 1 is mapped to b1 up to n is mapped to bn, right? So a function of this form is a permutation of this set 1 up till n, which contains the indices 1, 2, 3 up till n, right? So what is bn? So first of all, so if I write it in this form, on the left column all these indices appear in ascending order from 1 to n, and on the right, so this whole thing represents a permutation, and on the right all these b1 b up till bn are elements of this group 1 till n of this set of indices, right? So first of all, let me ask you, can any of these bi's be the same? Any of the two bi's be the same? Let's say if b3 and b5, can they be the same? And b1, let's say b1 and bn, are these the same? Can any two of them which appears on the right column here, Can any of two of them be the same? And the answer is obviously no, because a permutation is an onto function, right? On one-to-one and onto function. Since it is an one-to-one function, which means that if it appears twice, if the same numbers appears twice in this column, then two different elements are being mapped to the same element. So which means that it is no longer one-to-one, right? So since it is one-to-one, therefore no two elements can appear, no two same elements can appear here. So each of these elements on the column on the right here are different from each other, and obviously these are n elements, 1 to n. So 1 on the left column, these are these are n indices, right? And on the right, each of these n indices are different from each other. So therefore they are just a different arrangement of these n indices. On the right, on the n, we have the arrangement of the n indices in ascending order, but on the right we have an arrangement of these indices in some random order, right? So what is a permutation? So how many permutations are there of Sn? In Sn, how many permutations are there? So how many permutations of this set of indices from 1 to n are there? Right. So the question of how many permutations are there becomes a question of how many different ways we can arrange these BIs here on the right. Right, because as we just said, each B sizes are different from each other, and there are n of them. So it exhausts all the possible elements of this set of indices, and it's just a different arrangement of them. So how many different arrangements of the numbers from 1 to n are there? The answer is very simple. There are n factorial such arrangements. Right, so these are n objects, and there are n factorial different arrangements of these objects. So therefore, the number of elements of Sn, the number of permutations of a group of these indices, is n factorial. So the order of the group is n factorial. The order of the group Sn is n factorial. Okay, so we have talked enough about permutation groups. Okay, so last thing we talk about the composition of permutations. So if you are given two permutations f and g in cycle form, how do we find the composite of f of g? The answer is very simple, right? Very basic thing. F of g means first g and then f, right? So if you want to see, let's say we begin with 1. What is 1 mapped to by f of g? So first by g is 1 is mapped to 2, and then by f 2 is mapped to 5. So 1 is mapped to 5 by f of g. So we write 1, 5, and then 5 is mapped to 1 by g, and 1 is mapped to 3 by f. So 5 is mapped to 3, and 3 is mapped to 4 by g, and 4 is mapped to 1 by f. So 3 is mapped to 1 by f of g, and we close the cycle here, right? And now we see what elements are not there. So 2 is not here, so we begin with 2. So 2 is mapped to 3, and 3 is mapped to 4. So 2 is mapped to 4, and 4 is mapped to 5 by g, and 5 is mapped to 2 by f. So 4 is mapped to 2 back again. So we close the cycle here. So any other elements remaining? No. We have all the 5 elements here. So f of g is this permutation in the cycle. Very simple. Now another thing. So if we are talking about a finite group, which means it has a finite number of elements, and a finite number of elements, it has a reasonable number of, right? Not a really large number of elements for which we cannot draw group table, right? It has a finite number and a small enough number of elements, we can draw group table. So in theory, we can draw group table for any group which has a finite number of group elements, right? It will just not be practical, right? If the number of elements of the group is really large but finite. So such a multiplication table for a group of a finite group is called a group table or a Cayley table, right? A Cayley table is named after Cayley, who was a mathematician. So we talk about Cayley table. Cayley tables is just a multiplication table which consists of just all the possible products, right? All the possible products A circle B. A and B are the elements of the group. Then all the possible products A circle B are in the multiplication table for the group, which is known as the Kelly table. So consider the group of S2, a very basic group. S2, the symmetric group S2, right? It contains just the two elements. One is the identity permutation, and another is just one other possibility is a transposition, 1 2. And now we draw the group table. So on the borders, on the top and on the left, we write the elements in the same order, right? So the identity E and tau, and in the column as well, we write in the same order E and tau, and then in the body of the table, we write the result of E into E times E is E and E times tau is tau. In the first row, we see E times E is E and E times tau is tau, and the second is tau times E, right? Tau composed with E is tau, and tau times tau is identity composition. Okay, so this is a group table for the symmetric group S2. And in general, we read the Kelly table like this: if A star B is the binary operation of the group, and A star B is in the multiplication table, then A star B is a result of this is in the same row as A and the same column as B, right? This result of multiplying A with B, A star B, is in the same row as A and the same column as B. It's read like this. Now we turn to subgroups. So what is a subgroup? A subgroup is a subset of a group. A subset H of a group G is a subgroup of G if it satisfies the following properties. First is the closure properties, that for all AB in H, AB, the product AB is in H, and AB, the product, here is the binary operation of the group G, right? The same binary operation as the binary operation of the group. If the binary operation of H is different than from of G, then H cannot be a subgroup of G, although it may be a subset of G. So here the binary operation is we are talking about the same binary operation inherited from the group G. So if AB is in H, then A times B is in H. So this is a closure property. Then second is the identity element. The identity element of G is in H, and also H contains inverses of each of its elements. So if A is in H, then its inverse is also in H. So what does it tell you, right? So H is a subgroup of G. A subgroup of G is a subset of G, first of all, and this subset of G is also a group itself, right? So why is it a group? Because it satisfies all the three group axioms. First of all, it is closed under the binary operation of the group. So the binary operation is defined. And then the first property, this is associativity, is automatically defined because it is a subset of the group G, and the binary operation is also the same as that of G. So since the associative law holds for the group G, it automatically holds for the group H, for the subgroup H, right? So associativity holds, and second, the identity element exists. So the identity element of G is in H, identity exists, and the inverses also exist. Inverse of each element of H is in H. So therefore, it satisfies all the three group properties. So H is a subset of G, which is itself a group. Okay, so a subgroup of a group is a subset of G, which is itself a group, right? So and now we turn to some examples of subgroups. So one of the very basic example is the set of complex number of modulus 1, right? The set of all the complex numbers of modulus 1 is a subset of the group C star under the binary operation of multiplication. C star is the non-zero complex numbers, C minus 0, right? So all the complex numbers with modulus 1. The set of all these complex numbers is a subset of C star, and this is a subgroup of this group C star under multiplication. And I leave it to you. You should verify it yourself, the three subgroup properties, and you can do this by writing the the elements of this set. Since okay, so we can write complex numbers in exponential form, a times e to the I theta, and since the modulus of this complex number is 1, so a equals 1 here, and we can just simply write the elements of this set as a okay, we can write it as e to the I theta, right? So if we write the elements of this set as e to the I theta, we can easily just verify all these three properties, right? So it is closed. Obviously, we multiply two elements of the form e to the I theta, we get again the same element of the form, which is modulus 1, and so basically multiplying two complex numbers with modulus 1 gives another complex number with modulus 1, and the identity element is the number 1, the complex number 1. Does it have modulus 1? Yes, it has modulus 1, so it is in this set, and also the inverse of each of the complex numbers. So if you have the complex numbers of number of the form e to the I theta, then the complex number of the form e to the I 2 pi minus theta, right, is the inverse, and you can check it by yourself. I'm multiplying it with the number. Okay, so this group, this subgroup of the complex number is called a subgroup group for the obvious reasons, because a set of complex numbers with modulus 1 forms a circle in the complex plane, a unit circle in a complex plane. So if you picture it, all the complex numbers with modulus 1 forms a circle, a unit circle in the complex plane. So therefore, it is known as a circle group. Next is the subgroup of the general linear group, which is known as the special linear group, SLN. And SLN is a group of real n by n matrices. The real n by n matrices means matrices with real entries, with a determinant 1, right? So it is a subset of the group of invertible n by n matrices, right? So first of all, we have to check is it a subset of the group of invertible n by n matrices. So yes, and the answer is yes, because it has a determinant 1, and all the matrices with non-zero determinant are invertible. So all the elements of this special linear group are invertible, right? And now the properties 1, 2, and 3 you can verify it yourself. It's quite simple. And the closure property holds because if you multiply two n by n matrices with determinant group 1, so it will result in an n by n matrix with determinant 1 because of this property. Determinant of a times b equals determinant a determinant b. So if a has determinant 1 and b has determinant 1, then determinant of the product a into b is also 1, right? So therefore the product of two n by n matrices with determinant 1 is also an n by n matrix with determinant 1. So the closure property holds. And the identity element of G, is the n by n identity matrix. Does it have determinant 1? Yes, an identity matrix has determinant 1. So it is contained in this set, and also inverse of each of element exists. So does the inverse of each of the matrix in this set exist? So this set consists of n by n matrix with determinant 1. So obviously determinant 1 means non-zero determinant, so it is invertible. So inverses exist, and therefore it is also a subgroup of the general linear group, right? The general linear group is a group of n by n invertible matrices, right? And is also and by n invertible matrices, and with one like special requirement that the determinant has to be 1, and these are real matrices, right? Not the complex ones. They can be complex matrices with the complex entries, but in special linear group they are the real matrices. And also, okay. So the third property, the inverse, okay. If and if a matrix, let's say, if an element of the special linear group, so if A is an element of a special linear group, then A inverse obviously is invertible. So last time, so when I was discussing property 3, I forgot to check this property, which is essential for this property 3 to hold. So which is, if A is in this set, then obviously A inverse exists and also is in that set. So that I have proved. And for A inverse to also be in this set, it has to satisfy this property that it has to have determinant 1. So if A has determinant 1, does its inverse also have determinant 1? And the answer is yes, by the second property, the determinant of A inverse equals 1 over determinant of A. So if a matrix A has determinant 1, its inverse, which is also contained in the set, has determinant 1. So therefore, yeah, its inverse is also in the special linear group S1. Right. So all these three properties are satisfied. Therefore, we can say it is a subgroup of the group GLM. Right. And now we can easily see what are the two very obvious subgroups of a group. The two very obvious subgroups are the group itself G and a group with just one element, which is the identity element. So this is known as the trivial subgroup. So these two obvious subsets of G are the subgroups of G, and it can be very easily verified. So any other subgroup of G which is other than these two, one trivial group or the group G itself, is known as a proper subgroup of G. Okay, so we are done with that, and now we talk about one special subgroup of integers, right? So now we talk about subgroups of integers, right? The group of integers, right, is an important group, and it has to do with number theory. So in this section we deduce some results about number theory. So first of all, we begin with some important definition. So if A is an integer which is not 0, then the set of all multiples of A, which is a subset of Z, is denoted by ZA, right? So ZA is just a set of all multiples of A, where A is an integer, right? A non-zero integer. So ZA is A times K, such that K is an integer. The set of all of these elements A times K, such that K is an integer. And this is a subgroup of the group of integers, right? And I leave it to you to verify this. And so it's very basic and very easy to verify it. Just uses these three properties, right? These three subgroup properties, and it will be easily verified. Now, come our very important theorem, right? This is a very important theorem. So after we just study it, you should keep this in your mind. Let S be a subgroup of Z plus. Then either S is a trivial subgroup, which is just a group containing one element, which is the identity element, or it is of the form ZA, where A is the smallest positive integer in S. Okay, so there are only two possibilities. If S is a subgroup of an integer, then it has to be a one of the two, right? Either it is the trivial subgroup, and if it is not a trivial subgroup, then it has to be of the form ZA, right? Which means A is the smallest positive integer in S, right? And ZA is the set of all multiples of A. So we begin with the proof. If S is a subgroup of Z plus, then 0 is an S, right? Because it is a subgroup of Z, right? And subgroup contains the identity element. So 0 is an S. And let's say if 0 is the only element of S, if there is no further elements in S, then we are done. The set, then it will be a trivial subgroup of S. And otherwise, it will contain some other non-zero integer. And by the property of inverses, right? Since it is a subgroup, and inverses also, and its inverse is also contained in S. So minus S is an element of S. And since like n or minus n is positive, right? If n is positive, then minus n will be negative, and if n is negative, minus n will be positive. So one of n or minus n has to be positive. So S contains a positive integer. So S already contains a positive integer, at least one positive integer it contains. And now we denote A by the A denotes the smallest integer in S. So at least it contains one integer, right? So the smallest of them we denote by A. So now we show that ZA is a subset of S. So A is the smallest integer of S, and ZA, which is the set of multiples of A, is a subset of S. So first of all, we take an element from ZA, which is KA for some integer K, right? So first we consider these elements where K is positive, right? All these elements of the form KA where K is positive. So it is in ZA, and then Ka means add K to itself n times, right? And since A is in S, right? Therefore, A plus A is also in S, and by induction, we can also see that A plus A and plus A, and if you do it n times, it is also a member of S. So this A plus A plus A up till n times, which is equal to K, is an element of S. So this thing is very easy to see by induction, right? You use induction on the number of terms. This is A plus A plus A, right? Two terms it holds, and then assume it holds for n terms, and then prove it for n that it also holds for n plus n terms. Right? So K is an S. So this proves. Okay. So also we have the property of inverses. If Ka is in S, then its inverse, which is minus Ka, is also in S, right? So K is a positive integer, then minus Ka means multiplying a negative integer to A, right? So we have exhausted all the possibilities. So for all the positive integers we have seen, so by considering the elements of ZA, first of all, we consider all the positive elements by considering elements of the form Ka where K is positive, and then by considering elements of the form minus Ka where K is positive or minus K is negative, right? So it includes all the integers, all the non-zero integers in ZA, right? Is an S. And finally, we are just left with the zero integer, which is in ZA, and since 0 is 0 times A, it is in S, right? 0 is because 0 is a subgroup of Z plus, and subgroup contains an identity element. 0 is in S, and 0 can be written as 0 times A, right? It is an element of A. So this element of ZA is also in S. So therefore, ZA is a subset of S. So here, so far, we have proved that ZA is a subset of S. So I'm going here a little bit slow so that you understand, right? If I go it fast, then it can be difficult to grasp, right? Now, we will prove that S is a subset of ZA, right? So first, in order to prove that ZA equals S, first we have to prove ZA is a subset of S, which we have already done. And now second part is, now we prove S is a subset of ZA. So let's say consider an integer in S, then if you divide n by a, so a is a positive integer, which is the smallest integer of s. So if you divide n by s by a, right? If you divide n by a, right? So n can be written as n equals q times a plus r, where q and r are integers, and 0 less than equals r less than a. So r is an integer between 0 and a, including 0 but not including a. Right? This is basically the remainder theorem. Right? So it is quite obvious if you picture, right? If you divide n by a, if you just picture a set of multiples of a, right? 1 times a, 2 times a, minus 1 times a, minus 2 times a, 0. And if you picture this set, then you see that any integer n, you can reach it by just multiplying it with some integer and then adding to it an integer between 0 and a, right? This is quite obvious, but I'm not saying that since it looks quite obvious you should believe in it. Yeah, that's certainly not the case. It looks quite obvious, we can say yeah, it is most probably correct. But if in case you have not seen the remainder theorem, then I recommend that you go and see a rigorous proof of this remainder theorem. Right? It is important, not just based on your intuition and instincts to accept a theorem, but to at least see one time its rigorous proof. So if you have not seen the rigorous proof before, I strongly recommend that you go and check a rigorous proof somewhere. Right? So it can be, so if n is an integer in S, we can write n as qa plus r for some integers q and r, such that 0 less than equals r less than a. And now since ZA is a subset of S, so qa is in ZA, right? Is a multiple of a, integer multiple of a in ZA, and it is a subset of S, so it is also in S. qa is in S, and so since qa is in S and n is an element of S, so by the inverses, since S is a subgroup, so minus qa will also be in S. So n and minus qa both are in S, and therefore there's some, since it is a group, it is a subgroup, and therefore it is a group, there's some n minus qa which is equal to r from this equation. N minus qa equals r is in S, okay, by the subgroup property. And since a is the smallest positive integer in S, so a is the smallest positive integer in S, and r cannot be equal to a. It is 0. It is less than a, right? It is a positive. Is either a positive integer less than a, or it is 0. So r cannot be a positive integer less than a, because r is in S, and if r is a positive integer less than a, then a will not be the smallest element of S. So therefore r cannot be a positive integer, so there is only one possibility that r equals 0. So this remainder r equals 0 and n equals q times a, right? And n equals q times a, so n is an element of ZA, right? Because Z consists of all the elements of the form a times k, where k is an integer, and qa is also an element of ZA, and n equals qa since r equals to 0, so n is in ZA. So this shows, so we begin with n is an element of S, and then showed that n is in ZA. So we have proved that S is a subset of ZA. So now by these two things, ZA is a subset of S and S is a subset of ZA, we have proved that S equals ZA. So this theorem is proved, right? So again, I repeat this. This is an important theorem. It says that if S is a subgroup of integers, we are not talking about any subgroup, but any group, but a special group of integers, Z plus. So if S is a subgroup of integers, then either S is a trivial subgroup, right? Or if it is not a trivial subgroup, it has to be of the form ZA, right? Or which means it is a group. It is a set of the multiples of A, and A is the smallest positive integer in S, right? So this is what this theorem says, and we will use this theorem to deduce some important facts about integers, so which we see next. Now, first of all, we begin with this definition of the set ZA plus ZB. So if A and B are two integers, then the set S defined as ZA plus ZB, which is the set of the integers combinations of A and B, which is RA plus SB, for R and S and B being an integer. The set of all integer combinations of A and B, the set ZA plus ZB, okay, is a subgroup of integers, right? And I ask you to verify this, right? It is quite straightforward. The same three properties of subgroups you have to verify, and you can verify this on your own. It's a very straightforward thing to do. So okay, so we have defined this. Now if A and B are not both zero, then it can be written as Z times D, right? Since this is a subgroup of integers, right? And any subgroup of integers is either a trivial subgroup or a subgroup from D CZ times D, where D is an integer. So if both A and B are not zero, so this set ZA plus ZB cannot be the trivial subgroup. Yeah, it contains either A or B, which either A is non-zero or B is non-zero, right? So it contains a non-zero element, so it is not a trivial subgroup. Therefore, it has to be of the form Z times D, where D is the smallest positive integer of this set, and this D we call the greatest common divisor of A and B, or GCD A and B. And the reason for calling this the greatest common divisor will be evident by the next theorem, right? So we have a theorem here. So let A and B be integers, not both zero, and D be the greatest common divisors. Okay, so the greatest common divisor is the smallest element of the set ZA plus ZB, right? So so ZA plus ZB is a subgroup, since both of them are not zero. So ZA plus ZB is not a trivial subgroup, and it is equals to ZD for some integer D, and by the definition it is the greatest common divisor, and it is the smallest element of the group ZA plus ZB. So remember, the smallest element of the group ZA plus ZB, where A and B are not both zero, is defined as the greatest common divisor. Then the following holds: D divides A and B, and if an integer E divides both A and B, it also divides D. And now you see the reason why it is called the greatest common divisor. It is a common divisor, it divides both A and B, and also the greatest one, because if any integer E divides both A and B, right, it also divides D. So it has to be, if it is positive, then it has to be less than D, right? And if it is negative, then obviously it is less than D, right? So D is the greatest common divisor of AB. So the definition that we learned a long time ago, that the greatest number that divides both A and B is the greatest common divisor. Now we see that by defining it differently, right, in terms of this element of a set, right? We deduce this as a theorem that such a thing is a greatest common divisor, right? And number 3, there are integers R and S such that D equals to RA plus SB, right, which is quite an obvious property, because ZA plus ZB equals to ZD. D is in ZD, so D is in ZA plus ZB. So D is in ZA plus ZB means that D can be written as RA plus SB, right? It is quite obvious. But why do I state it? Because this just forget about groups now and look at this. Okay, so greatest common divisor is the greatest number that is the greatest number that is a divisor of both A and B, right? And this greatest common divisor can be written as an integer combination of A and B, right? This is a fact. So this is not an obvious fact at all, and this is an important fact. That's why I've written this as a third property. So this equation D equals to RA plus SB. It's not an obvious equation. If D is a greatest common divisor of A and B, then it can be written as an integer combination. This fact is not obvious at all. Okay, so third part is obvious and we have already proved it. So we go over this first and second part. So since A and B are in ZA plus ZB, right? A is in ZA plus ZB and B is also in ZA plus ZB, and ZD equals ZA plus ZB. So A and B, so this set equals ZD. So and A and B are in this set ZA plus ZB. So A and B both are in ZD, and A and B both being in ZD means A can be written as D times some integer. If A can be written as Z times some integer, it means D divides A, and also the same for B. B can be written as D times some integer, so D divides B. D divides both A and B. And so this is the okay. So this is the proof of the first part. Okay, so the second property I forgot to add the proof. So now I've added this proof, and so if E divides both A and B, right, then we consider this combination RA plus SB, and D equals RA plus SB, because we have already proved the third property that the greatest common divisor D can be written as an integer combination of A and B, which is RA plus SB. So if E divides both A and B, then it must divide this linear combination, because E divides A means that A can be written as integer multiple of E, and B can also be written as an integer multiple of E. So this whole thing can be written as an integer multiple of E on the right side. So therefore E divides D, right? So since E divides this combination RA plus SB, therefore E divides D, right? And we have proved the second property. Okay, now one application of the things that we have already learned. So we find the greatest common divisor of 314 and 136. Actually, this example is from the book of Michael Artin, Algebra by Michael Artin. So first we write 314 as this. Okay, so first we divide 314 by 136. So the answer is 2 and the remainder is 42. So we write it as 2 times 136 plus 42, and then we divide 136 by 42 and write it in the same form. So 136 is 3 times 42 plus 10, and again take the same two things, right, for 42 and divide it by 10. So 42 equals 4 times 10 plus 2, right? So why we are writing this? There is a reason for this. So using this first equation, we can see that any integer combination of 314 and 136, right, which is A times 314 plus B times 136, can be written as an integer combination of 136 and 142, and vice versa, because A times 314 plus B 316 equals 2AB plus B times 136, because 314 equals 2 times 36 plus 42, right? So it's 2A plus B, and 136 plus B times 42. So any linear combination or any integer combination of 314 and 316 can be written as an integer combination of 136 and 42. And similarly, if we have an integer combination of 136 and 42, so A times 136 plus B times 42 is, so we can write A as A equals 2B plus A minus 2B, right? Adding and subtracting 2B. So 2A plus B plus A minus 2B. So we have 2B times 136 plus A minus 2B times 136 plus B times 42. And this, if we just factor out B here, 2B times 136 and B times 42, factor B here, so it's 2 times 136 plus 42, which is equals 314. So it's B times 314 plus A minus 2B times 136. So we have written okay, so if So this linear combination as a linear combination of 314 and 136, right? And so this set is Z314 plus Z136 equals Z136 plus Z42, right? Because any integer combination, right? Any integer combination which is an element of this set is an element of this set, because any integer combination or can be written as an integer combination. Any integer combination of 314 and 136 can be written as an integer combination of 136 and 42. So this is a subset of this, and also this is a subset of this, because the converse is also true, right? So we have this Z314 plus Z136 equals Z136 plus Z42, and so since we know that's the smallest integer, right? Since both of these 314s and 136 are not 0, so the smallest integer of this set is the greatest common divisor of both 314 and 136, right? And since this equals the set Z316 plus Z42, both 314 and 316 and 136 and 42 both have the same greatest common divisor. So GCD 314 136 equals GCD 136 42. And similarly, from these relations, the first relation we have this, and similarly from the second and third relations, we can also deduce the greatest common divisor of 136 and 42 is equal to the greatest common divisor of 42 and 10. This follows from the second equation, okay, this one. And similarly from from the third equation, it follows that the greatest common divisor of 42 and 10 equals the greatest common divisor of 10 and 2. And what is the greatest common divisor of 10 and 2? And it is simple, it is 2, right? So this way we have found the greatest common divisor of 314 and 136, which is 2. So this way of finding the greatest common divisor is known as the Euclidean algorithm, right? So we have just used the Euclidean algorithm to find the greatest common divisor of 314 and 136, right? Which is quite an interesting application of this of all these things we have done so far, right? So now the definition: two non-zero integers, right, are relatively prime or co-prime if the only positive integers that divide them both is 1, right? So the only positive only positive integers that divides both of the integers. We are talking about two non-zero integers a and b, and there is only one integer, one positive integer, and that is 1, that divides them both. Then those integers are called relatively prime or co-prime. So this is the definition of relatively prime or co-prime. And now, okay, the corollary of the theorem. So the simple corollary of the theorem that we have studied is two integers a and b are relatively prime if and only if there are integers r and s such that ra plus sb equals 1. Which is quite a straightforward proof of this, right? So if a and b are relatively prime, this means the only integer, okay, the only positive integers that divides them is 1. And so if we consider this set za plus zb, the smallest element of this is 1, yeah, because the greatest common divisor of a and b is 1, right? And so za plus zb equals z, right? And since za plus zb is equals z, so 1 is an element of za plus zb, and if 1 is in za plus zb, so we can write 1 as an integer combination of a and b, that is ra plus sb equals 1 for some r and s and z, right? So now the converse: if ra plus sb equals 1 for some r and s, some integers, then Since Ra plus Sb is an element of Za plus Zb, right? It's an element of the set. It contains all the possible integer combination. It is one of the elements. So the smallest positive integer of Za plus Zb is 1, right? Because Ra plus Rb is 1 and it is contained in Za plus Zb. So 1 is an element of Za plus Zb, and this has to be the smallest positive integer because 1 is the smallest possible positive integer, right? And since the smallest positive integer of this set is 1, and the smallest positive integer of the set is also the greatest common divisor of A and B, right? So 1 is the greatest common divisor and hence the only positive divisor of A and B as required, right? So it's quite a simple proof. And another corollary, if a prime integer p divides a product ab of integers, right? So we are talking about a prime integer, not just an integer, but a prime number p, which divides the product a and b of integers. Then either p divides a or p divides b, right? One of these things are true. P has to divide a or p has to divide b. It is not obvious at all, right? It can be true like some integer like divides the product a and b, but does not either divide a or b, right? So it's not obvious at all. So if in case it is a prime integer p, right, a prime integer, then it has to be true that it either divides a or either divides b, right? And we see the proof of it. So it's another interesting proof from the group from number theory, right? That we prove using with the help of group theory. So let p be prime and assume p divides ab but does not divide a, right? Assume that p does not divide a. Then p being n prime, 1 and p are the only positive divisors of p. Okay. Therefore, the greatest common divisor of a and p will be equal to 1 because the only divisors of p is up here 1 and p. So the common divisors of a and p can include 1 and p only, right? Since p does not divide a, right, by the assumption, so p is not a common divisor. So only 1 is the only divisor of a and b, and the greatest common divisor of a and p is 1, and which shows that a and p are relatively prime. Yeah? A and b are both co-prime. And by the previous theorem, right? This previous corollary that if two integers are relatively prime, then their two integers exist, r and s, such that ra plus sb equals 1, right? So now since a and p are relatively prime, then their two integers r and s such that ra plus sp equals 1. And now we multiply the equation with b. Rab plus spb equals b, right? Since p divides both Rab and spb, right? P divides ab, right? We assume that the first line we assume p divides ab. So p divides Rab and p divides spb because it's a product integer multiple of p. So therefore it divides the sum, which is equal to b, right? P divides b, which is as required, right? So either if p divides the product, so either it divides a, and if it does not divide a, then it has to divide b. So we have proved this theorem, right? It's quite an easy proof. Not very easy, but looks quite an easy. And it's definitely a very simple proof. But assume, let's say, if you don't have group theory and you have to prove this fact on your own without using group theory. And this, the proof as it looks here, right? It looks quite elegant, somewhat elegant and somewhat simple, right? Might not look that simple and that straightforward if we do not use the concept of proof. Okay, so that illustrates some importance and some power of group theory, and what help, why does it help, right? Of introducing such structures. Right? So, what was the need of introducing a new structure in algebra that is a group, right? It's the work of humans, right? humans have introduced themselves a new structure in algebra, which is known as a group, right? So what was the need of doing so? And now we see the answer of this, right? These are the previous theorems that we have proved. All these theorems are not very obvious, and simply we can prove it simply using group theory, right? So especially these equations, d equals ra plus sb, is d is the greatest common divisor, then it can be written as an integer combination of a and b, is not obvious at all. Okay, so now we come to another interesting subgroup of Z plus, which is ZA intersection ZB, right? ZA intersection ZB, where A and B are integers. So, and I leave this to you to verify this fact, right? So you have to verify that ZA intersection ZB is also a subgroup of Z plus. It definitely is a subset because ZA is a set of integers and ZB is a set of integers, and intersection of a set of integers has to be a set of integers, right? So the remaining three properties are easy to verify, and you can verify this. And now assume that both A and B are non-zero, right? So since both A and B are non-zero, then their intersection will not be the trivial group, right? Because it contains AB, right? ZA contains AB because B is an integer and it contains all the integer multiples of A. It contains AB, and also B contains AB because A is an integer, and ZB contains integer multiples of B. So AB, which is not zero, since A and B are not zero, Z intersection ZB contains them, right? So it is not a trivial subgroup. And by this theorem, right, the first theorem which I asked you to remember, to keep in mind, right, that what are the only possible subgroup of Z plus? Either the trivial subgroup or the group of a form ZA, where Z is a smallest positive integer in S. So since it is not the trivial subgroup, so it has to be of the it has to be a subgroup of the form Z times some integer, right? So where are we? Yeah, so since it is not a trivial subgroup of the integers, it has to be of the form Z times M for some positive integer M, right? And we define this integer to be the least common multiple or of A and B, right? Or LCM AB. So why we call this least common multiple? It is clear from the next theorem, which is a very simple theorem, right? So Z intersection ZB is not a trivial subgroup, and we are talking about both integers which are both non-zero, right? Two integers A and B are both non-zero. Z intersection ZB is a non-trivial group. It has to be of the form ZM, and M is the smallest positive integer of that intersection, and M is then defined to be the least common multiple, right? So ZM equals Z intersection ZB. So this is the theorem. Let A and B be non-zero integers, and let M be their least common multiple, so that ZM equals ZA intersection ZB, right? Which is the definition of least common multiple. Then M is divisible by both A and B, and if an integer n is divisible by A and B, then it is divisible by M. Okay, so the first property says that M is divisible by both A and B. So M is a multiple of A and B both, right? And second property says that if an integer n is divisible by A and B, or if an integer n is a multiple of A and B, then it is divisible by M, right? So being divisible by M means it is greater than M. If it is a positive integer, then it is greater than M. So M is the least common multiple, right? By the obvious definition, what is a least common multiple? Is a common multiple of any A and B, which is the smallest one, right? So first property says that M is a common multiple. Second property says that it is the least because any multiple of A and B is divisible by M. So it is the least common multiple, right? M is the least common multiple of A and B. The proof is very obvious, right? I will leave it to you. So the proof we can do it. It's simple, right? What this theorem says is like M. Okay, so M is in ZM, right? So M is in ZM, which is equal to ZA intersection ZB. So M is in ZA. So M is in ZA means it is a multiple of A, right? A times some integer, we can write M. So M is a multiple of A, right? So M is divisible by A, right? And similarly, M is a multiple of B, is in ZB. So it's divisible by Z. So the property 1 holds. M is divisible by both A and B. Now, if an integer n is divisible by A and by B, so it simply means n is an element of Z intersection ZB. So n is divisible by A means n equals A times some integer, right? So n is divisible by A means n is A times some integer. So n is an element of ZA, and n is divisible by me means n equals B times some integer. So n is in ZB, therefore n is in ZA intersection ZB, right? Since n is in ZA intersection ZB and ZA intersection ZB equals ZM, so n can be written as a multiple of n. ZM is a set of multiples of n, and n is in this set. So n can be written as a multiple of n. So therefore, it is divisible by n, right? And that's the proof. It's quite an obvious proof. So now we end with the last corollary, right? The last corollary is D. Let D be the greatest common divisor of A and B, and M be the least common multiple of A and B. And A and B are the positive integers, right? Not only non-zero, but positive integers A and B. Then AB equals Dn. The integers, the product of integers AB equals the product of the greatest common divisor and the least common multiple. Obvious. So this theorem is not obvious, right? But it is simple if you use the previous theorems. Yeah. So the proof is simple. So D is the greatest common divisor of A and B, right? So B divides. So D divides B, right? So B over D is an integer. Since D is the greatest common divisor of A and B, so D divides B, and B over D is an integer, and A divides AB over D, right? Since B over D is an integer, so obviously A divides AB over D. Also, A over D is an integer, right? Since D is a greatest common divisor, is a divisor of A and B both, so A over D is an integer, and B divides AB over D. So just multiply A over D by B, right? AB over D is the number which you get by multiplying A over D by B. So B divides AB over D. Since M is the least common multiple of A and B, right? M is the common multiple of both A and B. So M divides AB by D, AB over D, right? M is the least common multiple. So since from the previous theorem, so any multiple of A, right? If n is any multiple of A and B, then M divides n, right? The least common multiple divides n. So these things, AB over D, right, is a multiple of A as well as it is a multiple of B, right? Therefore, the least common multiple M divides this AB over D. So by this is the previous theorem that we have studied, right? So far so good. So now M divides AB over D, and therefore dm, just multiply both sides by D. So if M divides AB by D, so dm must divide AB, right? That's obvious. So now we can write D equals to RA plus SB. D is the greatest common divisor of A and B, and the greatest common divisor can be written as an integer combination of A and B, right? So just get a look at this theorem. Yeah, if D is the greatest common divisor of A and B, then D equals RA plus SB for some teachers are in S, right? So I'm just continuously reminding you so that because it's new, so yeah, this reminding continuously makes things easier, right? So we can write D equals to RA plus SB. Then if you multiply both sides of the equation by M, so dm equals to RAM plus SBM, and both of these terms on the right are divisible by AB, right? Because right, M are in the term RAM, you can write M as some so B times some integer, right? Because M is a multiple of B, right? M is the least common multiple of B, so M is a multiple of B. So M is some integer times B. So this first term RAM will become a multiple of AB. So AB divides RAM and AB divides SBM as well, because we can write here M as a multiple of A, right? It's a least common multiple of A and B. So M equals some integer times A. So AB also divides the second term SBM. Therefore, since it divides both the terms, it divides the DM. AB divides DM, right? And now first we show that DM divides AB, and then we show that AB divides DM. So each of them divides the other, right? AB and DM both divide each other, and both are positive, right? So one important thing is positive. If one was positive, other was negative, then they may not be equal. But uh, since both AB and DM are positive, so AB has to be equal to DM, right? They both divide each other and they both are positive, so they both are equal as required. So this is the theorem. So with this we come to an end now, and yeah, so hope you have learned something from it, and I know obviously, yeah. Yeah, okay, so we have covered all. So see you next time then, and that's all for now, right? Okay.